Hey everyone. Last time we introduced the idea of power series. So remember, a power series is a series of this form right here. So it'll be sum n equals k to infinity, c sub n x minus a to the n. And the way you want to think of this is the right way to view it, is that it's a polynomial, or at least it resembles a polynomial, right? But it doesn't stop, right? It goes on forever. And to each power series, right, there is a radius of convergence and an interval of convergence. So remember, this x is a variable, and so you can substitute real numbers in for that variable, and then you can ask the question now. Once you've substituted, you have an honest, an actual regular infinite series, the one that we applied, or that we applied all our tests for, and you can ask the question, for what values of x does it converge or diverge? And so the interval of convergence is the entire set of real numbers for which the power series converges. And we learned that the ratio test is typically the way you want it to approach this. So let me do this example right here, just to kind of remind us. So this one goes like this: sum n equals 0 to infinity, x plus 2 to the n over 5 to the n. Now this one right here, so here's our power series. You could use either the root test or the ratio test. I am in the habit of just using the ratio test, but you could also use the root test on this one. I'm just going to go with the ratio test, but what I want to do is find both the interval, or both the radius and the interval of convergence. So ratio test goes like this. Compute the limit as n goes to infinity of x plus 2 to the n plus 1 over 5 to the n plus 1 times 5 to the n over x plus 2 to the n, all in absolute value. So what I did, I've already done the flipping and multiplying of the denominator when setting up the ratio test. And then we want to cancel, or we can. So this will be limit as n goes to infinity. Let's see, so we'll have absolute value x plus 2, so the x plus 2's cancel and leave us with 1 in the numerator, and then the 5's cancel to leave us with 1 in the denominator. This limit, right, is equal to absolute value of x plus 2 over 5, right? Once we canceled, there was no n left in the expression. The ratio test tells us that we need this less than 1, which means that we need absolute value of x plus 2 to be less than 5. And notice now we're staring right there. That is the radius of convergence, that number 5 right there. As soon as you get, right, when you're doing the process, when you get to an inequality of that form, right, x minus a less than some number r, right, then you're looking at the radius of convergence. So here we have x minus -2 less than, or absolute value, less than 5. Right, so the radius of convergence is 5. Now we also need the interval of convergence, right? So we need to check the endpoints. And so I want to unravel this, getting rid of the absolute value. So I have -5 less than x plus 2 less than +5. And then we solve. So this gives us x less than 3 and greater than -7. Okay, so the points that I need to check, right? Remember, the ratio test gives us no information when the limit is actually equal to 1. And that corresponds to these two places here. So that means that it could be convergent or could be divergent. We want to plug those endpoints back into the original power series and then use whatever test we need, right? Whichever test works to determine whether it's convergent or divergent. So we check the endpoints. And so first I'm going to look at x equals -7. When I plug it in to the series, let's see, if I put a -7 in here, what I'm going to get is -5 to the n over 5 to the n, which gives me sum n equals 0 to infinity of minus 1 to the n. This definitely diverges by test for divergence. So since limit as n goes to infinity of minus 1 to the n does not exist, right, the series, the series, so to finish this sentence, the series diverges by test for divergence. Okay, so now we need to check the other endpoint when x equals 3. Plug that in. So we get sum n equals 0 to infinity. When I put a 3 in here, I'm going to get 5 to the n on the top, 5 to the n on the bottom. So this is the series sum n equals 0 to infinity of 1, which means add 1 to itself infinite number of times. Definitely divergent. So since, once again, you can do it by the test for divergence, since limit as n goes to infinity of 1 equals 1, which is not equal to 0, the series diverges by test for divergence. So our conclusion then, we have interval of convergence is going to be, well, it converges for all real numbers between -7 and +3, but not at the endpoint. So the interval of convergence is -7 to 3, open interval. Right? It does not converge at either of the endpoints. And let's go on to another example now. So I'd like to look at this one here. So here's a power series. Sum n equals 0 to infinity of x to the n. Now, okay, so here's a power series. Its center is 0, so if you want to get technical, it looks like this. It's really 1 times x minus 0 raised to the n. And then the question is, does it converge or diverge? You could use the ratio test, you could use the root test, or, and this is what we want to do, is recognize that this should look familiar. This series converges for certain values, diverges for other values, and it would look more familiar, I think, if I wrote it like this. Sum n equals 0 to infinity of r to the n. Then you say, oh wait, that's the geometric series. I know that it converges whenever the absolute value of r is strictly less than 1. Well, that's what's happening right here. This series converges, and we know exactly what it converges to. All I did was write x instead of r. This converges to 1 over 1 minus x when the absolute value of x is less than 1. So what we want to do is recognize, this is the geometric series. It's a power series, but we can use the results that we have from previously to make the conclusion that it converges, and it converges to this function right here. And that's where we're headed. So what we have is the radius of convergence for this one is 1, right? R equals 1. Interval of convergence. You can check the endpoints. In fact, we already did check the endpoints long ago when we were first learning about this. It diverges when x equals plus or minus 1. And so the interval of convergence is minus 1 to 1. This is going to be one of our most commonly, we're going to use this particular power series constantly in the next week or so, maybe a little more than a week. So remember this result. In fact, we're going to start getting a list of familiar power series that you'll need to memorize. Now, one fact that we're going to need about power series, I guess I'll put it here. And I just want to get this one down on paper. We'll make a little more use of it later on, but I want to have it in place. So So if the power series and I'm just going to state it centered at 0, so sum n equals k to infinity, c sub n x to the n converges for absolute value of x less than r, and we have a continuous function, so let's say f of x is continuous, then a related power series, the power series that we get by substituting f of x in place of x. Right? So notice all I've done here, I took the function f of x and plugged it in for x. It turns out if you take a continuous function and substitute it into a power series, it will converge, so this one converges for any time that the absolute value of f of x is less than r. So when you substitute, it's going to change the radius of convergence, but you get the result of substitution when it's a continuous function, right, is a convergent power series. Okay, so now I'm about to write down the same thing that we had there, but I just want to sort of restate what just happened. So here's where we're headed. I want to take various functions and represent them as power series. And so we just had an example, and so let me just sort of write this down again. So from the study of geometric series, we have that 1 over 1 minus x is equal to the sum n equals 0 to infinity x to the n for absolute value of x less than 1. And what we say when you see this, so I mean, what does this mean? It means that if I take any number between plus and minus 1, plug it into the left-hand side and the right-hand side, we're going to get the same answer. We are guaranteed that the right-hand side converges to whatever we get on this side, right? So if I plug a 1/2 in on this side and this side, we're going to get the same answer. The way we say this is we say that the function, right, and notice this is a function, we say that the function has been represented as the power series. When we say that a function is equal to a power series, we say that it's been represented by the power series. So I can say, in other words, the function 1 over 1 minus x has been represented by the power series. And we'll see why that's going to be useful, but this is a very, very, very important technique in mathematics, right? If we can take a function and represent it as a power series, and then make use of our understanding of power series, right, we can get very important results, right? And we will see that as we go on. So our first step is to just sort of recognize that this is our goal. So let me write this down. Our goal is to represent functions as power series. So let me just start off with an example. And this is going to take some time to actually, we're going to develop various techniques for representing functions as power series. Right? So this will take a good deal of work. But let's just start with an example. We have at this point, we have exactly one function that we know how to represent as a power series. But from this, and from our previous theorem that tells us something about substitution, we will be able to represent other functions as power series. So, so let's let f of x equal, so this is going to be x over 2x plus 1, what we want to do is represent this function. So represent f of x as a power series and find the radius of convergence. And so let me just put it over here. So I'm going to use that. Let me just put it over here in a little box. So 1 over 1 minus x equals sum n equals 0 to infinity, x to the n. So I'm going to use that fact. Okay, so what do we have? We have x over 2x plus 1. I mean, it doesn't look exactly like this. What I want to do is manipulate things and try to make it look somewhat like this. So the first thing I can do, I need a 1 in the numerator, so I can pull the x out. And then this is equal to x times 1 over 1 minus a negative 2x. So inside the parentheses, what has happened? We had the function 1 over 1 minus x, and we've substituted negative 2x. So this is equal to x times sum n equals 0 to infinity. So I'm going to take the geometric series, and I'm going to substitute a negative 2x in place of x. Now, remember, when you substitute, the radius of convergence changes, and so I can say that these two things are equal as long as the absolute value of 2x is less than 1, right? This one holds when the absolute value of x is less than 1, so substitute a negative 2x in both spots right there. That means that negative 2x has to be less than 1, which I can obviously rewrite as absolute value of x less than 1/2. So that's going to be our radius of convergence. Now, let me clean this up. This is not quite in the form that I want. So continuing with equal signs, this is equal to x times sum n equals 0 to infinity. Negative 2 to the n, x to the n. And then one more step, I'm going to bring this x back inside. So if I multiply, what I'll get is sum n equals 0 to infinity, negative 2 to the n, x to the n plus 1. And so let me collect what we have now. Final answer goes like this: x over 2x plus 1 is equal to sum n equals 0 to infinity minus 2 to the n, x to the n plus 1, and this holds for all values of x for which absolute value is less than 1/2. Right? So by using this one fact that we know how to represent the function 1 over 1 minus x in terms of the geometric series, we can, by manipulation, right, represent other functions. So let's try another example. Okay, so let's find a power series representation for the function, so let's say f of x equal to x to the 4th divided by 4 plus x squared. And remember, let me put it back over here. right? So what we know is that 1 over 1 minus x equals sum n equals 0 to infinity, x to the n for all absolute value x less than 1. So I want to, by manipulating this function over here, I want to make it look like the function 1 over 1 minus x. See what we need to substitute to actually make this all work out. So first step, let's factor the x to the 4th out. Okay, next, let's see. I've got a 4 down there, but I actually wish that it was a 1. So I'm going to pull a 4 out of each piece in the denominator. So this will give me x to the 4th over 4. And then we'll have 1 over 1 plus x squared over 4. And then I see a plus sign there. It should be a minus sign. And so this is x to the 4th over 4 times 1 over 1 minus a negative x squared over 4. And now what we can see is inside the parentheses, we've substituted negative x squared over 4 in place of x. So I can write this out. This is equal to x to the 4th over 4 times sum n equals 0 to infinity, negative x squared over 4 raised to the n. And this equality holds as long as absolute value of negative x squared over 4 is less than 1. And let's simplify that a little bit. So what does that mean, or how can I rewrite that? That's the same as saying absolute value of x less than 2, right? Bring the 4 over, take the square root. Right, tells us that our radius of convergence is 2. And now let's just finish this off. We need to simplify this a bit. So this is equal to x to the 4th over 4, sum n equals 0 to infinity. Okay, so this negative, that's a minus 1. I'm going to write that as a minus 1 to the n. Then I have x squared raised to the n. That's an x to the 2n. And then in the denominator, I've got a 4 to the n. Now I want to bring this stuff back inside. So this is equal to sum n equals 0 to infinity minus 1 to the n, x to the 2n plus 4 over 4 to the n plus 1. Remember, when you multiply, you add the exponent. So x to the 4th times x to the 2n, give me an x to the 2n plus 4. And in the denominator, the 4 times the 4 to the n, give me the 4 to the n plus 1. So let me now collect everything that we have. And put the final answer right here. So x to the 4th over 4 plus x squared is equal to sum n equals 0 to infinity minus 1 to the n, x to the 2n plus 4 divided by 4 to the n plus 1. And I want to keep our radius of convergence. That's part of the answer, right? This equality is true for some values of x. Which values of x? It's those ones right there. So that is part of our final answer, right? Now, and one thing you'll notice, for when it comes to representing power series, or functions by power series, we typically don't care about the interval of convergence. We just care about the radius of convergence, right? So what you'll see is when I represent a function as a power series, I will include with it the radius of convergence, but I'm not going to go through and check the endpoints, right? We really care about the overall where it converges. We don't care about these two endpoints, right? Typically. Okay, so that's a good place to stop. We will continue our study of representing functions as power series in the next lecture. Okay, see ya.